So in this video, I thought I would show you how I typically take notes and study for an exam. I know in the last video I called it studying for probability exam, but and I didn't really show you much about how I actually study. Really just, what notes I'm looking at and how I kind of break apart things. I didn't go into super great detail because I really just wanted to show you what my favorite theorem was. So I will show you a little bit about what is expected of us to know. Now for the probability exam, it is on Tuesday, which doesn't really give me much time to get caught up on the stuff. But it's really everything that's in this packet. So central limit theorem and the Berry-Yassine bound. So I keep saying so a lot. I need to work on that. But this is a list of topics that our instructor gave us and what is expected of us to know for the exam. He's got it listed into 3 categories. The first category is definitions. There's really no excuse for not knowing the definitions. And he has 3 listed. So we have convergence and distribution. And he's drawn this arrow. I mean, I copied what he wrote on the board, but he drew this arrow connecting it to use continuity theorem to prove the classical central limit theorem. And he's got proof written next to it with a star, which means that we do need to know the proof of the central limit theorem. And it uses the continuity theorem to prove it, which has this idea of convergence and distribution. And I remember at the beginning of the semester, we didn't cover new material. We kind of reviewed material from last semester, I guess, to put the new stuff into proper context. So that's why he's making us do this again, even though we did it we did it last semester. There was a question on the test that was basically prove central limit theorem. So I guess he's making us do it again. After that, we should know the definitions of these. So these are 2 new definitions that we've learned this semester: asymptotic negligibility and Lindeberg's condition. And I'll show you what they are. So in the notes, that's L2 negligibility. Where's asymptotic negligibility? Here it is. Here's the definition. A matrix of d-dimensional random vectors is said to be asymptotically negligible if the following statement holds. So this is really the definition. And I typically like to write the epsilon condition over here first. So I'll say, like, for any epsilon greater than 0, you have that the limit as n tends toward infinity of the supremum of 1 less than equal to k, but still finite, of the probability of the absolute value, or in this case, I guess the magnitude of the d-dimensional random vector xnk is greater than 0, is equal to 0. Or greater than epsilon is equal to 0. There, I stumbled through that sentence, but you can see it. So you can see in the symbol notation, it's a lot cleaner than writing it out, word for word. That's why mathematicians like their symbols. I like to say that in the English language, there's over 1 million words easily, but in mathematics, there's like 500 words. And you get to actually define some words, just as long as it's properly defined in the context in which you're dealing with stuff. Like, for example, when I was doing research at my previous institution where I got my thesis, or I got my master's degree and I was writing my thesis, I remember I needed a word to describe these certain sets that I was playing with, and they were subsets of tiles. So I was looking at tiles in the complex plane, and these tiles were self-similar. So I wanted to talk about the subsets that were similar. They were scaled down. They were scaled down copies of the original tile, and I needed a word to describe them, and I didn't have a word for it. So I defined the word subtile. I know that's kind of a not very interesting, getting to define your own word situation. But it was a word that I needed, and I got to define, and I put it in the paper. So it feels kind of weird and also kind of cool to be able to define your own word and then people accept it. I think it happens in mathematics a lot. Just as long as it's properly defined and it makes sense in the context, then it will be accepted. So that's one definition. The other one that he said we needed to know was Lindeberg's condition, which is right here. It's highlighted. I actually did not highlight all of this stuff. My office mate thought that this packet was hers, and she highlights everything. So she highlighted this bit here, and she goes, "Oh no, this isn't my pack of notes." So anyway, not that I'm mad or anything. So what does Lindeberg's condition say? We have a family of matrices. Hold on. No, it's a matrix of d-dimensional random vectors. It's kind of weird to see that his notes talk about matrices of, or not matrices, but d-dimensional random vectors. Everything we do in class is single dimension, but his notes is always in d dimensions. That means when I go back over and I review these notes, I always reduce it to the one-dimensional case, because that's everything we do in the class is one-dimensional. Okay, whatever. So you have a matrix of d-dimensional random vectors, and fnkx is the CDF, which stands for cumulative distribution function of the random vector xnk. We say that the matrix satisfies the Lindeberg condition if the following statement holds. So it says here that the limit, as n approaches infinity, of the sum, as k tends from 1 to infinity, of the integral on this really tiny set, or not tiny set, but the set of all vectors such that the absolute value of x is greater than epsilon, of the absolute value of x squared times the differential of the distribution function according to the random vector is equal to 0, and that's true for any epsilon positive. It's kind of a, out of proper context, you look at it and you're like, what in the world is this thing? And why does it matter? Because it's so specific. It has proper context as, okay, it makes a lot of sense if you have the proper context. So if we go back to the big list, under theorems, he says that we need to be able to prove the classical central limit theorem. It's not too long to prove, but you have, just be careful with it. As long as you have basic algebra skills and you know this one trick at the very end, it's not that bad to prove. The second thing we need to know is Lyapunov's theorem with the standardization step, and we need to know Lindeberg's theorem, as well as the Feller extension. So those two really go together, Lindeberg's theorem and Feller's extension, which is this theorem here, Lindeberg-Feller CLT. And here you can see that we have, it's essentially the central limit theorem, but under different context. All right, so what does it say? You have a collection of d-dimensional random vectors such that for each fixed n, this collection consists of independent random vectors with mean vector 0. And you let sigma n be defined as the sum of the expectations of these random vectors being multiplied by one another. And they converge to a non-singular matrix sigma. I think that in the one-dimensional case, this reduces to a more easy to comprehend statement. The reason I'm not explicitly stating why is because I don't really know. I have to go back over and read it and figure out exactly, because you're not gonna have to worry about the non-singular part if you're only in the one dimension, I believe. But again, I have to review my notes. So we define Zn to be the sum of random vectors for fixed n. So you fix this in and then you add up all the random vectors in the single row. And then you get the big payoff, what the statement's all about. It says here that the following two statements are equivalent. The matrix satisfies Lindeberg's condition, which is that guy, if and only if the Zn's converge in distribution to the normal distribution and the random matrix consists of asymptotically negligible random vectors. So that's where the two ideas come into play, the Lindeberg definition and the asymptotic negligibility statement, because they go hand in hand down here. Without the asymptotically negligible part, then you can't make this statement. Exactly. And then you have Lyapunov's. I'm probably pronouncing that wrong. I think it's Lyapunov, maybe. Where is it? Oh, here it is. It kind of says the same thing, but then it differs by this last sentence. If gamma n, which is defined to be the sum of third moments, so the expectation of a random variable raised to the third power, well, okay, you raise the absolute value to the third power first, and then you take the expectation. That's called the third moment. If you sum up those third moments and they tend to 0, that sum tends to, well, okay, as n tends toward infinity. So you think of this as a sequence. If that sequence tends toward 0, then you know the zn's converge in distribution to the normal distribution. And he did tell us that he might make us know the proof, which means I'm probably going to have to go through the proof of this a couple times. And I'm going to actually show you the nitty-gritty of it, but I'm not going to beat you over the head with it, because that's just going to be really boring. Which goes up to here, exercises. We should know all homework problems, plus any evil thoughts he said that he might come up with. I'm a bit scared by that, because it's hard to be able to apply this stuff when you don't have very many examples. And it's kind of hard to find examples that are specific to this, because we're learning stuff that's very specialized. It makes it a lot more challenging. And I almost forgot, we got to know the Berry-Yassine bound. He did tell us, though, that he won't make us know the proofs for Lindeberg's theorem and the Berry-Yassine bound, because apparently those are really difficult and very time-consuming. Oh, for example, let's look at Lindeberg's theorem. You can see here that he starts here with proof, so you can get an idea of just like the process. He screams verify here. I don't really know why. Again, these are his notes, so it looks like he's writing a book, but he's putting like comments off to the side, like you need to fix this before you publish the book. Anyway, so here's the step 1. Takes care of the converse. And this is more of the proof. I believe he did this in class, and it took a long time. And step 1 ends here, and then step 2 picks up here. A lot of good stuff, as you can see. And why does he have 2 step 1s? Oh, I think the first 2 steps are proving this direction, and so this step 1 refers to, yeah, you can tell that I haven't really read through his notes. I did take notes over his notes, though, but I skipped the proofs, because I don't really think it'll help me to write that proof down. Plus, he says he's not going to test us over it, so I'd rather spend my time doing something more useful that's going to get me a good score in the test. Anyway, step 1 for the other direction starts here. You can see that it keeps going on and on and on. And where does it end? Step 2, another truncation happens. Step 3 is down here. It just keeps going. Step 4, Kryman Netley. This proof just won't end. Lyapunov's. Step 5. And then here's the end of step 5, and then boom, little spade to tell you where the proof ends. So you can see just how many pages it took for him to prove the Lindeberg-Feller extension theorem. And then below it we have the Berry-Yassine bound. And apparently this proof is also quite long. Well, here he has it as a remark. But the Berry-Yassine bound, well, there's a proposition. I don't think that's the real bound, is it? I don't remember. I remember it being stated explicitly. I think it's this one, Essene's inequality. If this integral is finite, then this previously defined delta is less than or equal to this dude. I think that's the Barry-Essene bound. It's been about a week or so since he talked about it, and it was new at the time, and the proofs was complicated. What does this proposition say? Let Zn be as in Lyapunov's. He spelled Lyapunov wrong. With the same assumptions and notations, if the characteristic function of Zn is phi n, then the absolute value of t times the cube root of gamma n is bounded above by 1/2. Oh, wait, if that happens, then we have this statement. Seems awfully specific. Oh, never mind. Here it is. Explicitly stated, just like I thought. The Barry-Essene bound. If in Lyapunov's central limit theorem, if gamma tends towards 0, then the supremum of the probability of Zn minus phi x, which is the standard normal distribution, is less than or equal to c, some absolute constant, times gamma n. Which doesn't look like it takes too long to prove. I think it's just that there's a lot of propositions and claims that need to be shown in order to wrap it all up. I think that's probably what he's referring to when he says the Barry-Essene bound's too long to prove. But he does say that we need to know it. I'm not entirely sure what he's going to ask us to do with it, but which kind of scares me, because I don't really see a whole lot of examples in his packet, and that scares me. I need those examples in order to do stuff. If it's not too complicated, I might just read through the proof a little bit and see what I can do with it. Okay, so let's actually, I don't want this video to go on much longer. So let me just show you something that I will do when I prepare. I'll start with something easy. Always start with something that you know you can do with no problem. So definitions are easy. So you can just write down the definitions a bunch of times until it starts to sink in. So what does convergence and distribution say? So I believe, I have to double check, but I believe, if I remember correctly, we have a sequence of random variables, and we have a random variable x, we'll call it. Then xn converges in distribution to x if the distribution functions fn. So each xn has its own distribution function, which I label fn. And we say that that sequence of functions converges to f, which is the distribution function for x, at the points of continuity of f. And I always forget that second part here, this part where this is pointwise convergence. So fn is the corresponding distribution function for xn, and f is the distribution function for x. So the definition of xn converges to xn distribution means these functions converge to this function pointwise. And I always forget the next part where I say, where is it converging? It happens at the points of continuity of f. I cannot speak. And I have to double check this definition, but I believe this is what it was. It's been a slight minute before I've seen this, last time I saw this. So I got to make sure that I haven't messed that up. But what I'll do is I'll take this, if this is right, I'll just write this like 20 times until it becomes, natural for me and I don't have to think about it anymore. And then if we're doing, asymptotic negligibility, what I'll do is I might read the first part, but it's really the second part that I'm most interested in. So to put it in symbol notation, I would write for any epsilon positive, the limit as n tends toward infinity of the supremum of the set probability xnk greater than epsilon is equal to 0 for k finite. Or I can write it this way. So I'll just write that sentence or this statement here like 20 times until I don't have to think about it anymore. It might be useful to write it in a slightly different way. Like if you're used to the definition of, convergence, like a sequence of functions that, or sequence of anything that converges, you might be able to write it this way. For any epsilon positive, there exists an n natural number such that for any n greater than or equal to n, we have that the supremum k greater than equal to 1 probability x little n k bigger than epsilon is smaller than epsilon. So we might write it this way. And this isn't in his notes, but I kind of generalized this statement to this statement because I noticed that this piece right here looks a lot like convergence in probability. And if you're in real analysis, it looks a lot like convergence in measure because the two are the same thing because probability is a measure. But this is another way of writing it. And then the last definition that we need to know is Lindeberg's condition. So it says here, I probably should write out the extra stuff. So we have x and k random variables. They have their associated distribution functions. So I'll write CDF of x and k. So those are just the preliminaries to make sure I'm not being dishonest. And then we write down the definition. Limit n tends toward infinity. Sum k equal 1 to infinity. Integral x bigger than epsilon. Absolute value x squared. Differential f in k x equals 0 for any epsilon positive. And I might try and write this in another way like I did up here if I really wanted to. But as long as I know the definition, I'm happy. And then I would just do this like 20 times. So I'd do this 19 more times and then I'll call it quits. And then I'll just do the exact same thing for the theorems. And I'll just keep doing it and doing it and doing it until eventually it becomes like I'm reciting the Pledge of Allegiance or something from grade school. And that's kind of how I do it. And just hope that he doesn't become too creative with these evil thoughts. So I told him to eat a big breakfast, something good, so that he doesn't get put in a sour mood. Hopefully that will be beneficial to me and him. Anyway, that's kind of how I study. If you have suggestions or you want to offer any knowledge about how you study for mathematics, I'm all ears. I hope this was useful to you. I hope you were able to learn something from this, I guess. I don't know. I've been in college for so long that it's really the only thing I know. But again, I only do the thing that works for me. And no one really does teach you how to study. You just kind of have to figure it out for yourself. Just figure out what the instructor is looking for. That's the best thing that you can do. Anyway, this video is long enough. See you in the next one.